Hello, this is Gary LaRue, Technical Editor at Microwave Journal. Welcome to today's EDICON online workshop on University Vitrig, a new mmWave evaluation kit based on a unique RFIC from VEAR. This workshop is sponsored by MiniCircuits. Before we begin, let me introduce you to our online platform. In the center of your screen, you'll see a window containing the presentation. To better see the slides, you can enlarge this to full screen. The window labeled Resource List contains a copy of the presentation and other resources. The workshop will be available to view on demand later, which will allow you to watch it again and recommend it to colleagues. Today's presentation will be given by Damian Hoffman of MiniCircuits. To read his biography, please open the biography box in the lower left corner of your screen. After Damian's presentation, we will have time for questions, so if you have one, just type it in the Q&A box on your screen at any time. Damian, I'll turn the session over to you.
Hi, thank you so much. Thank you all for attending. So what I want to speak about today is the Vitrig-74 system. Basically, the Vitrig-74 system is a new tool, quite revolutionary, that incorporates our highly integrated RFIC technology and radar OP into a small package you can take and play with. It actually gives you a mmWave radar at your fingertips. You can just take it, play with it, and start understanding the possibilities and capabilities of mmWave imaging and sensing applications without having to build your own system from scratch. Building a mmWave system from scratch is expensive, is time-consuming, spending huge amounts of effort on calibration and just getting it to work. What we're offering is a packed solution that you can just start and play with. So what is actually the Vitrig-74 system? The Vitrig-74 system is actually a radar on chip. It includes 20 transmitters and 20 receivers, onboard antennas, all being fed from a single RFIC, from VEAR's unique centipede chip, which enables you to transmit and receive signals anywhere within the 62 to 69 gigahertz range. Basically, it means that you can take this system and through a very basic and easy API, which we'll go over in this presentation, you can start and getting direct IQ data from all these pairs and actually start playing with the concept of MIMO radars in mmWave directly from your laptop. You will get all the fuzzles for each frequency point swept, which means you can start developing your own imaging algorithms on top of that. So let's take a deep dive into the actual system. So the Vitrig-74 system, you can see on the left side of the screen the schematic of the system. So the system is basically composed of a controller, which enables you to connect to the system through a USB, which goes to the radio and signal generator and processor. Basically, we have here a full radar chain, meaning we have the PLL and the VCOs and the mixer and the dial converters and the samplers all in a single chip. And the chip itself is divided into two parts. The first part is used to generate the actual waveform we're going to transmit. So you can see that block on the left side of the scheme. And this waveform is being fed to up to 20 antennas. So all of the antennas can transmit, meaning you can get diversity angular-wise in the transmission. And on the other hand, you have 20 receivers. Again, each one of the receivers can receive independently, which means you can sample the signal from each one of those 20 antennas. They go to the digital front end, they are being sampled, and what you get at the end is an actual IQ data per frequency point per antenna pair, which means that now if you want to start playing with coherent imaging, with machine learning, with whatever you feel like that you can do if you only had a mmWave radar, MIMO radar available, you can start doing that now. If we move to the second image, we can see the front end of the device. So you can actually see the antennas themselves. Each one of the golden rectangles is actually a separate antenna being fed by a separate port. So you can see that the array itself is an L-shaped array with one leg consisting of the transmitting antenna and the other leg of the array consisting of the receiving antenna. When looking at the effective virtual array created by this kind of array, you actually get a full rectangular array giving you very high resolution both in the elevation and in the azimuth axis. On the left image, you can see the backside of the device. You can actually see where the power supply goes. It uses external power to make sure you're not limited by the USB port. Has the USB port for communication. And at the center of the system, you have a YARS unique chip, enabling you to transmit and receive multiple ports in the mmWave region. If we're looking at the system specifications, just to go over them real quick, you can see that we have 20 transmitters and 20 receivers. We've seen them before. You can play with the frequency band from 62 gigahertz up to 69 gigahertz. So that means you actually have available up to 7 gigahertz of data you can record. You can control the RBW, which means the amount of time you spend on each frequency point. This will have implications both for the SNR of the system and for the scanning time. The shorter the RBW, the longer time you're going to be spending at each frequency point, the better the SNR will be, but the sweep time will increase. You can play with is the actual number of points. So you can decide how dense you want to sample those 7 gigahertz, for example. You can choose anywhere between 2 to 151 points, which means that you can actually play with the frequency sampling for different scenarios. If you want to see further ahead, further away, and you need to have a higher non-ambiguous range, you can just increase the number of points or reduce the bandwidth. It's all basically in your control. We're giving you the full API to realize your idea about what the radar can do. The minimum frequency step is 150 megahertz, and the ARP of the system is -5 dBi. So when looking at the system, we are planning the system to be compatible with the worldwide requirements for this kind of system. So you don't have to develop on one system, and once you want to do something else, you need to change all the parameters. The system itself is aligned to the global idea about what mmWave transmission should be like. If we're looking, let's say, at the 7 gigahertz complete band, you can get up to 2 centimeters of resolution. That's unparalleled resolution in terms of what the radar can give you. And the maximum angular resolution is about 6 degrees. Again, very high resolution, enabling you to do significant applications in the field of RF imaging. The antenna effective beam width, or the field of view of the antenna, is about 170 by 80 degrees. The antenna themselves are not symmetrical. The E-plane is a bit wider, about 170 degrees, while the H-plane is a bit narrower by around 80 degrees. That means that if you want to change the application, you want to see, let's say, wider field of view in one other direction, you can just rotate the board and build your own application over that. The way we control the actual, what we call recording profile, is spread into 2 parts. So the first part is, as we described here, you select the actual frequencies you want to scan, the bandwidth, the number of points, and the RBW. And the next step you have to do is you need to decide on the recording profile, which antennas are going to be transmitting at each step. Let's go over those profiles. Basically, the IMAGEVK-74 offers you 3 possible profiles with different number of transmitting antennas. In all cases, all the receiving antennas are used, so you always have 20 receives antennas. But what changes between the profile is how many transmitting antennas you have at each time. Basically, we have 3 modes of operation, which are divided by application through balancing the use case and the frame rate. So the first one is what we refer to as the low rate. In the low rate application, all the 20 antennas are transmitting, which means that you get the highest possible resolution in both axes. As we discussed earlier about the effective virtual array, the resolution is created by the combination of transmitting and receiving antennas. So what happens is, let's assume we put the board at such an orientation where the receiving antennas are spanning the azimuth direction. Okay? So regardless of the numbers of transmitters, you always get the full resolution in the receiving direction. So if you put the receivers on the azimuth direction, you always get the highest resolution on the azimuth direction. To get the resolution in the elevation direction, you need to scan through multiple transmitters. So what basically scanning through 20 transmitters allow you is to get very high resolution 3D imaging in both axes. So we can achieve that 6 degrees resolution both in the azimuth and the elevation. Now, as in always is in life, nothing comes for free. So to do that, we need to scan more antennas, which means that the frame rate is lower. So this is a very good usage for, let's say, static or semi-static targets. If you want to go to faster moving targets, then we can go to the med-rate profile. The med-rate profile has a somewhat different trade-off. The number of transmitting antennas is lower. You can say it's 10, so it only has half of the resolution in the elevation axis. However, the frame rate is much higher as we are scanning less. So it is a good balance. Let's say if you want to have good elevation resolution, say about 15 degrees, but you want to scan multiple targets or maybe slow moving targets. The last one, what we refer to as the high rate, is actually the opposite of the low rate, right? You have a very low number of transmitting antennas. You have 4 transmitting antennas, which means the angular resolution is somewhere around 30 degrees on the elevation. Again, the azimuth has the same resolution regardless of the profile because we are using all the receivers all the time. But what this gives you is a very high frame rate. So this is very good mode for, let's say, 2.5D imaging, meaning that you want to get high resolution in the azimuth direction, but you are willing to compromise for resolution in the elevation in return for faster frame rate. This is a good profile, for example, to be trapping people inside the room. You just want to know where they are. You want to be able to separate, let's say, ceiling, floor, and people. So you need a moderate elevation resolution, but you can probably get away with not having the full resolution. However, it's important in this use case to actually scan fast enough to track the people. So we feel that these 3 imaging profiles really give you a span of possibilities of things that can be done with this sensor. Again, we tried not to sacrifice at least one axis. You always get the high resolution on the azimuth axis, but by choosing the profile, you can switch between faster scan time and better elevation resolution. So you can actually span all the applications that the radar can do, from the very low resolution, very fast frame rate ones, to the very slow, let's say, to the slow rate, very high resolution one. So once we understand the parameters we can actually play with, let's go ahead and talk a bit about the actual API. So environment-wise, we have APIs as an SDK available for both Windows and Linux operation systems, and we have both Python and MATLAB SDKs you can connect to and just start a very simple recording flow. Basically, you only have to do 3 things to configure the system. You have to decide on the profile, which means deciding on are we going to use the high rate, medium rate, or slow rate? You have to define the frequency span. Which frequency you want to start, which frequency you want to end, what's going to be the number of points. Once you do that, you just give the system a command to start recording, and you can now acquire the IQ data through another single command. So basically, all you need to do is three commands: configure, record, get. And now you have the fuzzles you can actually play with. We offer the fuzzles in one of two modes. The first one, which is probably more applicable to most users, is an already calibrated fuzzles up to the antenna input. That means you don't have to do any de-embedding. All the de-embedding is done in the SDK, and you can actually start your algorithms and your processing from the point at which you're actually measuring the S parameters of the outside world. The other one is non-calibrated, which is for more advanced users who want to get the raw signals and see what they can play with. You get, and it's important to understand that, you actually get the S parameters of the channel as they are being measured in the millimeter wave. You get the full IQ data, meaning phase and amplitude, so you can start doing coherent imaging or any other algorithm which you feel might be useful. Obviously, you can get the antenna locations, so you can start doing the coherent imaging just from scratch. It takes basically 10 minutes to connect the board, set up a sample, and start seeing the fuzzles on your screen. So, can be done with this kind of system. So, possible applications are almost endless. Anything that you can do by transmitting and receiving electromagnetic waves and sensing them, you can do with this system. Starting from high-resolution 3D imaging. As we mentioned, you can get very high resolution. So if you're using the low-rate profile, you can actually get very high-resolution 3D imaging in millimeter wave, and you can start seeing the world around you in a whole new way. You can do people monitoring and accounting. One of the nice things about radar is, although it has, in a millimeter wave, enough resolution to track people and see the posture and track speed, these sort of things, it doesn't have any privacy violation issues because it's not a camera, which means that you can start developing applications that can monitor people in a room, see where people are going, how people are behaving inside the room, what's their daily life like, all using millimeter wave technology, up to things like gesture recognition, using machine learning to get all this vastly rich data. We're talking about, let's say, 150 frequency points for 400 pairs, feed it into your own favorite machine learning algorithm, and see what you can start doing with it. Basically, this kit and the way we think about it should allow you to start sensing the world in a whole new way without having to go into the hassle of actually building your own millimeter wave system, right? So what I want to do next, I want to look at one example. What we did is we did a simple recording of a metal ball in front of the device. That's a standard way to see sanity and see that the device is working. And I want to show some results and walk us through what we can see there. Okay. So what we can see here are actually two graphs derived from a single measurement. What I did in this case, I basically took a IMAGEVK-74 board, connected it to my laptop, and used the sample code you can see to get the IQ data. And then I placed a small metal ball about 10 centimeters from the device. And what I did there, and then I did two things. The first one, I said, okay, so I have all the 400 pairs, all the 151 frequency points. What am I going to do with them? So what I did is something which is very well known in array processing theory. I use a steering vector. So you take a steering vector. The steering vector gives you the phase change or the phase delay required per antenna pair. Once we move to an effective array framework, we can think about the pairs of the transmitter and receiver as creating a single virtual location in space, which can be thought of having a single, let's say, monostatic antenna. So I took those locations and I calculated the steering vector, which means the phase delay required between each one of those virtual array elements to get the best possible processing gain at the ball site, which means directly in front of the device. And what you can see here are the two graphs. The blue graph is what would happen if I would do non-coherent summation over those signals, meaning I would just take the amplitude of the signals after shifting them in phase and sum them up. So what happens here? So you can see at the 10 centimeter we have a target, right? That's the ball I put there. But overall the noise floor, which we can see at longer times, is quite high. And we can see some signal that remains at short ranges due to the fact that signals were not summed coherently. Okay, that means that we were not using the phase information we have in the signal to actually get all the processing gain. Now, once we do that, we steer all the phasors to the right direction and we sum them coherently, you can see the red graph. So the red graph basically has the same ball at the same location, but we can actually see that by coherently summing all the signals, we can get a much lower noise flow, right? Because now we're actually gaining the factor of the coherent summation. We can see that the signal at the beginning, at the very short times, has now been cancelled because it was not in phase between the different pairs. Okay? One of the nice things about coherent summation, you can actually get rejection for things which are not in the steering direction. And we can actually see at around 20 centimeter another reflection, that is the ceiling above the sensor. So we can actually see that the dynamic range is now much higher once we do the ball side steering. So that was steering for one direction. Now, what would happen if we were to take steering vectors for all the direction in space, both in azimuth and elevation, do the same thing and try to combine them to a 3D image? So we can see that in the next slide. So what we can see here is multi-angle steering. What I did, I just took all the possible directions and created an image with each, let's say, each angular direction being the graph we saw in the previous slide. So what we can see here, we can see an actual 3D image created by a mmWave radar. So the leftmost image is the angular image, meaning elevation by azimuth, and we can see the ball at the center with the side lobes, which are expected because I didn't do any tapering on the pairs. If I were to add any tapering on the virtual pairs, I could play with the central beam width with regard to the side lobes. And we can see on the other two slides the range versus azimuth and range versus elevation, and we can actually see again that we have side lobes in the range direction as expected because I didn't do any windowing on the frequency domain. So to get that, what I basically did, I took the sample code which comes with the VTrig, I added multi-angle steering, and now I can do mmWave 3D imaging with very high resolution just sitting next to my table. So the IMAGEVK-74 will basically enable you fast and easy access to a MIMO system working in the mmWave regime. You don't have to build your own system, you don't have to connect cables, you can just take it, plug it in, and have a radar at your fingertips. working in 62 gigahertz. All the signals are given as IQ data, which is basically the lowest level of raw data, meaning that you can start developing your own algorithms on the data itself, be it from coherent imaging up to machine learning algorithms. You can basically start and play with the data. We have a lot of ideas for what can be done. We're hoping you're going to surprise us. And the API, we try to make it as simple as possible and can be easily integrated into your own existing either MATLAB or Python project. So the whole idea of the VTRIG-74 is that you can start working and running and creating your own amazing things with mmWave MIMO imaging systems. Just let your imagination run free and show us what can happen when you find new ways to see the world around you. So I want to thank you so much for tuning in. I hope you enjoy this as much as I enjoy daily the VTRIG-74 system, and I would be more than happy to take your questions. Anything else you have, please visit us. We are more than eager to see what amazing things you can do with this system. Thank you so much.
Thank you very much, Damian, for a very interesting presentation. It's amazing the capabilities that are available in this system. We do have time, as you noted, for questions, so we want to invite our viewers to ask a question or two. If you have something you'd like to learn more about the system, just use the Q&A box on your screen. We'll see if we can get to as many questions as possible. One question I had watching this, and I may have missed the point that you made, but can you talk a little bit about the data rate? Is that tied to the up to 800 kilohertz sampling rate?
Hi, can you hear me?
Yes.
Okay, great. So the actual sampling rate of the system is related to the time it takes to sweep over all the frequencies and then get the data to the host. The 150 kilohertz I mentioned is actually the RBW for each frequency, which correlates to the time we spend on each single frequency. So the system is a step CW continuous wave transmitting. It means that we spend some known RBW on each frequency. We collect the phase and the amplitude of the channel we are measuring in that frequency, and then we save it as IQ data. So the update rate is actually related to both the number of frequencies we use and the profile. As I think I mentioned, the different profiles differ both in the number of transmitters and in the frame rate. The more transmitters we have, the more transmittings we are going to do. Let's say if I'm moving to 20 transmitters, then each one of those transmitters is going to transmit all the frequencies, and then I'm going to move to the next transmitter and transmit again. So while the update rate of the system is related to the RBW, it should be multiplied also by the number of frequencies, the number of transmitters, and some overhead on getting the data from the system. Typical numbers you can expect, let's say in the mid, are around 10 frames per second.
Okay, that's helpful. So would that be consistent with the application you talked about where you're maybe looking at people in a room? Maybe you want to monitor if someone falls?
So, yeah, from our experience, around 10 frames per second is a reasonable rate to do people tracking in a room, and generally, let's say, targets which are moving at around 1-2 meters per second can be tracked with the 10 frames per second system.
Very good. And you mentioned a couple times toward the end that you're interested to see what kinds of applications that people put this system to doing. What's the best way for people to tell you that information, how they're using it?
So basically, we're very eager to start interacting with our customers and to start seeing what people can do. We don't have, I think, yet any official forum or any official group, but we'll take that into account to see if we can get something like that done.
Yeah, as you say, you'll probably get a lot of good information. Well, I think we're out of time for questions, so let me thank you again, Damian, and MiniCircuit, and all our sponsors who make EDICON Online possible. A reminder that Damian's presentation has been recorded. It will be available to watch on demand. It'll be up within about an hour. You'll find it at the events section of the Microwave Journal and the Signal Integrity Journal website. So if you'd like to see it again, or if your colleagues would benefit from this workshop, please let them know and stir interest in exploring some of the applications of this device. And please join us for our next technical session, which will address MIMO radar for vehicles, presented by radar icon Eli Bruckner. Thanks, everyone.
Thank you.